Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you understand what a quantity called inductance is. Let me get it written up here. What is inductance? Well, for starters, I'll just talk about this. It's a property of circuits. We're going to consider this circuit right here for a few minutes. And I'm just making up some nice, easy values here so we can chat about. So we're going to imagine this circuit that's got powered by a 12-volt EMF, and we're not going to worry about the internal resistance of the voltage source there. We're going to imagine it's hooked to a 2-ohm resistor. And we're going to chat about what happens when we close this switch now. So when the switch is closed, we're going to get a current, and it's going to be in this direction as defined by positive charge carriers everywhere in the circuit. Now, if I were to ask you, like what is the value of that current? This should be a little longer there. And hopefully most of you or anybody watching this video could get me a number here. If you write a loop equation for it, 12 volts minus IR equals 0. And if you solve that for the current, you get 6 amps. So I did a graph over here, and I put this in blue. Although the units were a little hard to see, so I'm going to go ahead and 6 amps. Now, what we're going to chat about is this part of the graph right here. Like, when you graph that, it kind of makes it look like it's truly instantaneously 6 amps when you close the circuit. But that's just not how stuff works. Before that current can get the 6 amps, it's got to get through 1 amp, 2 amp, 3 amp, 4 amp. So the graph really, in reality, is probably more like this. And what we're going to be chatting about now is this stuff here. Now, if we had a circuit, and this was the actual circuit, just a loop here, it would hit that 6 amps so fast you wouldn't be able to even measure a time difference. But again, not truly instantaneously. There is some sort of time frame here. I'm going to call it delta t here, where the current is changing. Now, another thing to consider is this. So if you're in my class right now, we've been talking a lot about magnetic fields and what causes them. Currents cause magnetic fields. So if you just kind of mentally grab the wire right here with your thumb in the direction of the current, and then I were to ask you what direction is the magnetic field in the interior of this loop, you should conclude about like this way, what I would generally call plus K direction. Grab the wire right here, thumb in the direction of the current. Or here, thumb in the direction of the current, or here, thumb in the direction of the current. And you should come to the same conclusion, that the magnetic field vectors are this way in the interior. I'm just going to draw some of them here, right? Now, what that means now, right, we've got a magnetic field and there's a cross-sectional area here. So we also have a magnetic flux. And because we're looking at the time frame here where the current is changing, it stands to reason that these magnetic field vectors are changing, and therefore the magnetic flux is changing. So if the current's increasing, the magnetic flux is also increasing. Okay, Faraday's law of induction now comes into play. Induced voltage, remember, is equal to the time rate of change in magnetic flux, right? Change in flux over change in time. So this current, which produces these magnetic fields, which are changing, effectively creates its own voltage in the loop. Now let's talk about the polarity of that voltage, right? That comes from, we're going to get from Lenz's law, remember, which is nature hates a change in flux. The induced voltage will always produce a magnetic field to oppose the change. Now, these magnetic field vectors are this way. They are in what I would generally call the plus K direction. They are getting stronger. So the induced magnetic fields need to be this way to oppose the change in flux. And if you ask yourself, what current direction gives a field that way, right, that actually would have to be like this. So the polarity of the voltage, and it doesn't matter where I draw this in this picture, I'm going to draw it right here. The polarity of the induced voltage looks like this. Right, so this is the induced voltage. I don't mean to say there's an actual battery there, but the changing current produces a magnetic field, which produces a changing magnetic flux, which basically creates this voltage in the opposite polarity. Now, that voltage right there, all right, let's kind of mathematically talk about this. So the magnetic flux, remember it's, let me just say this, it's proportional to the field strength, and the field strength is proportional to I, the current. So it doesn't take too much mathematical messing around here to realize that this expression is directly proportional to the rate that the current changes. The proportionality constant here, I'm going to call it L here, that is what your inductance is. This is how I like to define inductance, right? It is resistance to changes in current. When a circuit has a very high inductance, it means it's very difficult to change its current. When it has a very low inductance, it's very easy to change the current. The units on inductance, well, you can see it right here, right? Since your inductance, let's see if I actually solve that, it's right, voltage times delta T over your delta I. So this has units of volt seconds per amp. And again, this is an I in the bottom. Sorry, all right, change in I. And of course, like most things in physics, a volt second per amp has its own special name. It's called a Henry. Okay, so what is inductance? It's resistance to changes in current. What are its units? Well, right here, volt second per amp. What's causing it? It's caused because of this, because currents create their own magnetic fields, right, which produces this, what I'll just call back voltage in the circuit. And what does it basically do? Well, it fights changes in current. That's why over here, it takes a little while for this current to get up to speed. Now, inductance itself, like what does it depend on? All right, so remember, right, it's coming from the idea of this, Faraday's law of induction. And by the way, I should probably put absolute values here to make this thing stay right here. What I mean by that is usually you write Faraday's law of induction with a minus sign here, and I'm not worried about that. We're just talking about polarities only. And you'll see it's flux dependent here, right? So when we think about flux, right, BA cosine theta in general, and I'm writing that kind of in a loose form here, you'll see that it's area dependent. So it's mainly geometric. It has to do with geometry. Obviously, the larger the area, the larger the flux, and against the larger the inductance. Okay, now one super easy way to increase the area, and now this picture will come into play, is if you just have many, many, many loops. So this picture is representing an iron core with some wires around it. This is the type of geometry that would have a very, very high inductance. The more loops you would have, the larger the inductance. The iron makes it larger because of what we discussed in class about magnetic domains lining up, and I'm not going to get into that right now in this video. So this actually is kind of like the symbol for an inductor. I'm going to go ahead and actually put that in the circuit. I'm going to put it in the place of this EMF here. Oh boy, I think I have to go adjust my eraser a little bit, but let me have to shrink this thing down. We don't need the N. There. So inductance is a circuit property that describes how easy it is to change the current in the circuit. Let me go over to my graph now. The blue graph here in this picture, whoops, represents like basically right here what would happen if the circuit had a zero inductance, like identically zero. You'd close the switch and the circuit would be 6 amps instantaneously. Now it's not actually possible, but that's kind of what that would mean. The green represents, the circuit's got a reasonable inductance, so it takes some sort of reasonable time frame. In my picture, it's like from here to here to get up to the 6 amps. And then I'll do another one here. This in this nice light blue. If the circuit had a very high inductance, or a much higher inductance, it would look more like this, right? Meaning it would take a long time, a pretty large delta T, to get to the maximum current. So other things about inductance that are kind of important, well, there's a symbol for it. This is the general symbol for inductance. How you calculate the voltage across an inductor is important in a lot of problems. So the voltage across an inductor is L delta I over delta T. Now this is written in what I call college algebra type of language. In the language of derivatives, it's L di dt. In an algebra-based course, the math for solving the problems is a little beyond the scope of the course. In a calculus-based class, you would go through and write equations to describe them. Mainly what I focus on is the kind of fundamental short-term and long-term behavior as they relate to circuits, and the inductor's effect on it. So anyway, I hope that this video has given you a reasonable idea of what inductance is, how it affects the circuit, and what it's caused by. Right? Have a great day.